Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, today I'll show CFD Conjugate heat transfer analysis using ANSYS Fluent fault-tolerant meshing. This is the model. This is consisting of some pipes, and at the top of this pipe some kind of heating surface is provided. Through this pipe we'll be providing freon gas at a lower temperature, and the top surface will be maintained at a constant temperature. To understand the geometry, let us cut this one from a specific plane. You see, this is the pipe, and surrounding this pipe we're having one heat source, which one will provide a constant temperature of 50 degrees centigrade, and through this pipe we'll provide freon at a temperature of minus 50 degrees centigrade. In this analysis we'll see the temperature distribution through this pipe. By the same time we'll see pressure and velocity distribution also. Okay, so for starting this simulation we need to save this model as FM database or with the extension of FMD. So let us close it, and we need to start Fluent launcher. Initially you have to select ANSYS Fluent fault-tolerant meshing from here. Next to that we need to import that CAD model, and here in this case, while importing these things, we need to select the custom mode, and then we can select that model. We need to drag this component into meshing model. We need to mesh all the parts separately. So we can copy the settings to child objects. Let us create meshing objects. So this is the component. Next to that we need to identify what type of analysis it is. It is an internal analysis. So with the default settings of internal analysis, we should move on and describe the geometry. Next to that we need to provide some cappings, because in computational fluid dynamics we need to have a closed volume. For that the opening spaces should be filled up with caps. And here in this case we are having two different openings. This is entry and this is exit, that to be capped, right? And zone type will be velocity inlet or mass flow rate. Let us provide the naming of this one as entry 1, and we'll select the inlet surface. So we can see here one cap is provided at the inlet location. After that cap should be provided at the exit location, and zone type will be definitely pressure outlet, as it is the exit, and we're keeping the name of this one as pressure outlet 1. Let us create cap at the exit location. You can see here two caps have already been provided at the inlet and exit locations. Next to that we need to identify regions. That means we need to identify the fluid domain. In this case we are having a single fluid, and that will be freon, which will be passing through these copper tubes, and at the top of this one we will be providing a heating source, which will provide a constant temperature at the top surface, right? Now for providing fluid domain we are having different options, and we will select offset method for providing fluid domain. Let us select entry 1, and at the entry we can see one diamond shape is available, and to locate the fluid domain we need to push that diamond inside this pipe. That can be done using offset. It will be done in the Z direction, right? So it will be in the negative of Z. Let us provide minus of 30. Enter. Now that diamond shape has gone inside. We can check it from section clippings. So this is the diamond. That means this one is providing fluid domain, or you can say domain for freon. Let us identify this region. That is known as fluid region 1. Next to that we need to identify some void domain, which will be away from this fluid domain, that is needed to restrict the movement of flow from inside to outside. So next to that, we need to create some kind of void domain which will be away from these tubes. And for that, we can select the whole assembly of the conjugate heat transfer, and this diamond shape should be away from this domain. So we can provide a offset value of this one in the y direction. Let's provide the value of y to be 50, and see this diamond will be moving up. You can see its actual location. Diamond is away from this zone. This will be indicating void domain, right? Let us identify this void region. Done. In this case, we have created two zones. One is fluid zone, another is void zone. Excluding that one default solid zone is created. Next to that, we need to define leakage threshold. In our model, we are not having any kind of leakage, so we can update this one with the condition of no leakage. You can see here three different domains have been created. One is solid region, one is void, another is fluid. This is required to mesh different parts separately. In this case, we don't require to mesh void zone. We need to mesh solid as well as the fluid zone, and we are considering polyhexcore mesh for both the cases, for solid as well as for the fluid. Let us update regions, and we'll select default meshing control options and update this one. Next to that, we need to generate surface mesh with the surface mesh target skewness as 0.8. By the same time, from advanced options, we'll select separate contact pairs to be made on, so it will be yes, and global minimum will be considering as 1. Let us generate surface mesh. Surface mesh is generated. We can see here. Let us see all zones. Now it is showing the overall summary of mesh as average skewness is 0.02 and maximum skewness is 0.83, and it is showing phase count is 1,27,976. And by the same time, you can see that it is having one inlet and one pressure outlet. By the same time, it is having some walls. To all the walls, heat will be transferred by convection with a specific convective heat transfer coefficient. Let us update these boundaries. Next to that, we need to add boundary layers. In this case, we'll be reducing the numbers of boundary layers. Instead of 3, we'll make it 2, and let us add boundary layers. Next to that, we need to generate the volume mesh, and in this case, we are considering quality improvement level as 0.04. Let us generate volume mesh. You can see volume mesh is generated. This is the segmented view of this mesh. You can see the complete view, and you can have a segmented view from different sections. Let us cut a little bit more and see inside. So this is the mesh. Next to that, we need to check the quality of mesh. From overall summary, you can see that quality of mesh, which is less than 0.1, is 1, and minimum quality of mesh is 0.079, and cell count is 1,18,501. We can check the mesh quality from here. It is showing that minimum orthogonal quality is 7.87 into 10 to the power minus 2, and maximum aspect ratio is 4.9 into 10 to the power 1, which is okay, not good one. So next to that, I'm going to switch into solution mode. At initial stage of solution mode, we need to define the units. Let us consider length to be as millimeter, and temperature will be considering as degrees Celsius. Let us close it. It is a steady state analysis. Next to that, we need to select models, and as it is a heat transfer problem, so energy equation should be on, and it will be viscous, K-epsilon to turbulent model, realizable and scalable. Next one, we need to provide materials. In this case, we are considering Freon as the fluid that will be obtained from Fluent database. We're considering Freon 12, copy, and solid we want to be made up of copper. Copy, close. So material is selected. You can see fluid is Freon and solid will be copper. Next to that, we have to define fluid domains, that is cell zone conditions need to be defined, and we know that fluid should be made up of Freon. That should be defined here. Apply, close. Next to that, we need to define solids. It is also made up of copper. That we define here. Apply, close. Now we need to apply boundary conditions. At inlet, we will provide Freon at a lower temperature of minus 50 degrees centigrade. Let us consider velocity of Freon as 0.001 meter per second. That means from this one, Freon will be passing at a very low velocity of 0.001 meter per second, and temperature of this one will consider as minus 50 degrees centigrade. Apply, close. At outlet, it will be having atmospheric pressure, or you can say it will be zero gauge pressure. Apply and close. We need to check the walls very carefully. At the heating surface, we need to provide a constant temperature of 60 degrees centigrade. This is the heat surface. So we need to provide a constant temperature of 60 degree, and that is made up of copper. And temperature, it will be 60 degrees centigrade, and wall thickness we are considering as 0.01 millimeter. Let us apply and close, and we'll consider all the other walls will be transferring heat by convection. So let us see this wall. This wall is made up of copper, and from this wall it will be transferred by convection with a heat transfer coefficient of 20 watt per meter square degree Kelvin, and temperature will be 30 degrees centigrade. And we're considering wall thickness to be 0.01 millimeter. Let us apply and close. The remaining walls should be also provided same boundary conditions, so we can copy this boundary condition and that to be applied for the remaining cases. We need to apply all the similar boundary conditions to the different walls. Copy. Same boundary condition is applied to the remaining walls also. Let us close it. Next to that, we need to select solution methods. As it is a heat transfer problem, we'll consider this one as coupled, and special discretization method we'll consider as Greenberg's node based method. Pressure will be second order, momentum second order upwind, turbulent kinetic energy will be again second order upwind, turbulent dissipation rate also it will be second order upwind. Next to that, we need to start initialization, and we're considering hybrid initialization here. Let us initialize. Hybrid initialization is done. So finally, we need to run the calculations. In this case, we are considering 200 numbers of iterations. Let us calculate this. Iterations have already started. Let the iterations move on. Whenever it is finished, we'll see the results and go for analysis. Calculation is complete. Now we can see the results, and results can be viewed from here. And initially we'll see results from reports, surface integrals, and we're going to see facet average, and our task is to see temperature distribution at the exit level. Not only at the exit level, we want to see temperature distribution throughout this body. So we can see at cap 1, that is inlet, cap 2 at the exit. Excluding that one, we want to see temperature distribution at all the different zones at the heating surface, and throughout all the body we want to see temperature distribution. Let us compute. You can see the results here. Cap 1, that is at the inlet, we have provided freon at a temperature of -50 degrees centigrade, and at the cap exit we can see the temperature is 59.79 degrees centigrade. Heating surface is also having temperature of 59.99 degrees centigrade, and different walls it is having different temperatures, and net temperature is 50.87 degrees centigrade, right? We'll see these variations through different contours. First of all, we'll see path lines, new path lines, and we're to see dynamics of flow particles through this model. And we're going to see all this distribution through all the surfaces. Let us display. You can see here temperature distribution through the pipe. Initially temperature was low, and we can see in a better way. Let us make this one a little bigger. Initially temperature is in the range of -50 degrees centigrade, and finally at the exit level also temperature is in the range of 50 to 59 degrees centigrade. Let us close it. Next to that, we're going to see different contours of temperature and pressure. New contours, and we're going to see temperature distribution throughout the body and also the fluid domain. Let us display. It is showing temperature at different locations. So it is maintaining higher temperature of 60 degree almost all the surfaces, but inside it is having different temperatures, you can see. And it will be better to see the temperature distribution from a specific plane. We'll see this one later on. And when you see the temperature distribution for this fluid domain only first. So another contour plane, when you see only temperature distribution for the fluids, new, and contours of temperature, and you want to see for the fluid body only. Let us display. This is for fluid body. You can see temperature initially at the starting level, temperature is very less. It is in the range of -50°C, and as it is approaching towards the exit location, its temperature is increasing, and finally at the exit level, its temperature is in the range of 60°C. Right? As we are providing constant heating at the top surface with the plate, so by conduction it is gained on these pipes, right? Next to that, when you see some other things like velocity distribution and pressure distribution also through contours, you're going to see pressure distribution through the fluid domain only. It is showing that at the inlet location, pressure is very high, and as it is approaching towards the exit location, its pressure is decreasing, and it was confirmed with the boundary conditions. At the exit location, pressure was 0 gauge pressure. Next to that, we're going to see velocity distribution also through this fluid. You can see velocity distribution, it is exactly same, it is not changing at all. Throughout this fluid body, velocity remains same. Next to that, you want to see something else like mesh. And you want to see only the faces, nodes and edges we don't want. So this is the mesh. Next to that, when you see something else like we want to have a scene between the mesh and the different contours of temperature and pressure, right? So we'll create a scene. Let us create a scene, and we want to create a scene in between mesh and contour 2, and in this case we'll make the mesh to be transparent for better view of these contours. You can see here the mesh is transparent. Through this mesh you can see how the fluid is flowing, and this is actually pressure distribution through this mesh, and we can view temperature distribution also. Let us cancel this. This is now actually velocity distribution with mesh, and first one is temperature distribution. Let us see temperature distribution with mesh. This is the first one for the whole body, and number 2, this is pressure distribution through this mesh. We'll see the results again. Surface integrals, and we're going to compute all the temperatures at different zones. Let us compute, and we can see this one from this console, and it is clearly visible that temperature at the cap 1, that means at the inlet, it was -50°C, and at the cap 2, at the location of exit, temperature is in the range of 59.79°C, and heating surface its temperature is 59.99 degrees centigrade. And all these are applied from boundary conditions. This is to have a comparison only, and we can have temperature of walls as 51 degrees centigrade, 52 degrees centigrade, and whole body average temperature is 59 degrees centigrade. And for the fluid region, we can see average temperature is 23.39 degrees centigrade, because at the inlet temperature is very less, it is minus 50 degrees centigrade, and at the exit it is 59.99 degrees centigrade. And at the outlet we can see the temperature is actually 52 degrees centigrade, and inlet temperature is minus 50 degrees centigrade, so the average temperature of fluid is 23.39 degrees centigrade, and the net temperature is 50.87 degrees centigrade. Okay, so this is all about our today's analysis. This is a very simple analysis. This is a conjugate heat transfer analysis using ANSYS Fluent fault tolerant machine. Okay, thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.